Hello everybody, welcome to this video where I'm going to be discussing CCNA version 1.1 chapter 1. The first chapter of the updated CCNA book, which is written by Jason Gooley and Randall Odom. So this will be giving an overview of what's covered in the chapter. So getting the key points, not covering obviously not covering it literally word to, obviously we're not literally going through every single thing mentioned in the chapter, but capturing the essence of the chapter here. So what we're going to be covering, well, first we're going to be having a look at the networking protocols that existed and were used before TCP/IP became prominent in the 1990s. We'll be looking at that, then having a look at a comparison between the OSI model and the TCP/IP model, and then having a look at the 5 tiers of the TCP/IP model. So that's what we're going to be doing in this video. So firstly, let's have a look at what networking protocols that were in existence before TCP/IP became prominent. Well, it's very interesting. First, before we look at that, it's very interesting to even ponder that and think that there were other protocols being used before TCP/IP's prominence. That even TCP/IP, can you imagine? There was a world without reliance on just TCP/IP. You had other protocols, you had alternatives. That was, the more you ponder, the more interesting this sounds. And it was an interesting time for networking before the 1990s, where you had Apple Talk being used for Apple Macintosh computers, and IPX SPX, which was created by Novell. And if you have used Windows 95, Windows NT, you would have seen IPX SPX. One of the options you could have configured your network with. You also had NetBEUI, which was created by IBM. And again, if you interacted with Windows NT, you would have seen NetBEUI as one of the options. So these existed alongside TCP/IP, but TCP/IP ended up becoming the industry's main protocol in the 90s, and then that's led us to where we are today. And now, when we look at the OSI model and compare that with the TCP/IP model, OSI model was originally destined to be the model that was going to be used in the industry. This was, this was created and it was intended to be used as the industry's standard. However, it had a standard first, code second approach, and that actually didn't help it compared to TCP/IP, which had a code first and then standard second a code first standard second approach, which made it more which gave it the edge, and that contributed to its popularity, and TCP/IP ended up becoming the model that we used in the industry today. And so what you got to remember though is that there was an old TCP/IP model, and now we've got this newer version of the TCP/IP model, which borrows from both models here. So you can see the data link and the physical layer are inherited from the OSI model here, and so whilst it went away from this link layer, this combined link layer that it had, which was covering both of these individual layers, physical and data link. The link layer covered both of them. TCP/IP, the newer model, borrowed from OSI model in that respect, so it took from the OSI model, and the rest of the model pretty much stayed the same, other than changing the name from internet layer to network layer. So also borrowed from OSI in that aspect. So from 4 tiers we went to 5 tiers, and that's the TCP/IP model that we use today. Now, if we look at the individual layers of the TCP/IP model, firstly, the application layer. What is the application layer? Well, the application layer is the layer that the user interacts with. It provides services to the application on the computer. And now we're going to look at HTTP. So good old HTTP, Hypertext Transfer Protocol, was invented by Sir Tim Berners-Lee in the early 90s. Now, Tim Berners-Lee it really paved the way for modern internet browsing. He really did a great service for the industry, because he gave web browsers the ability to request and receive for web content from a server. Now, today's something that sounds like something that sounds like something so normal, so common, but this was something that had to be invented, and Tim Berners-Lee is the one who's credited with inventing this functionality, and this has led the way for the modern web browsing that we all enjoy today. So this is basically what HTTP does, and this is the kind of the backstory behind HTTP. Now, HTTP codes. Now, it's important to know these codes. 200. The 200 code is the OK reply or return code. So when an HTTP request is initiated, a server replies with a 200 OK code. If it can return the request, if it can successfully return the request. However, if it can't, then we get the 404 web page error, or a web page wasn't found error, which I'm sure you must have encountered whilst browsing the web. So that's HTTP. Now, if we just have a look at this diagram here, which basically illustrates what I was talking about, HTTP, you can see this HTTP header here. Now, you see, in this case, we've got this laptop here. Now, this is, we're going to say this is Karen's laptop. Now, Karen wants to order a pizza. So she wants to order a pizza, but she needs to firstly get onto the web page which has the menu for her local pizza restaurant. So she initiates a request for that web page from the restaurant's web browser. Now, what happens is the request is received, and the server attempts to send back the menu, the web page. So it returns a 200 OK code, which means that the request is, which basically means OK. And we can see, so that's in the header, and then the data actually contains the web page content. So we see here menu.html, and then here we see another message here, which contains more web page content. Now, that's in a nutshell HTTP GET request and reply. Now, did you notice something about that second HTTP reply? Have another look. Well, the HTTP header was omitted. So if you look back here, you can see, whilst the first reply didn't included a header, the second one didn't. And that's done for a particular reason, because HTTP is clever. It's not going to continuously send repeated headers when there's no need. In this case, there's no need. It's just sending more and more of the web page content. So so it doesn't see a need to continue to say okay. So okay, here's your menu content. Okay, here's your web page content, your menu content. Okay, here's your menu content. Yeah, okay, here's your menu content. It doesn't see a need to do that. It's not necessary. So the OK header is omitted, and we just send the web content, which makes a lot more sense than the former. So that's basically what HTTP. Now moving on to the transport layer. Now, what is the transport layer? What does the transport layer do? Well, the transport layer provides services to the application layer protocols that reside one layer higher in the TCP/IP model. Okay, so you've got the transport layer now, and then you've got the application layer sitting on top. Now, the transport layer is providing services. Services is and I will see the transport layer in action now. So this is one special feature of the transport layer here, is error recovery. So if you see this, now if you look at Karen's request again for that web page containing the pizza restaurant menu, we can see that here in the replies, first we've got okay, we can see that 200 OK return code. Then we see the menu content. But what's this here? This is the sequence number, and this is what TCP has, and this is to track the delivery of what we call segments. So TCP communicates in data units called segments. So we can see that this second one wasn't received by Karen's laptop. So Karen's laptop notices this, and so what happens is it requests segment 2 to be sent again. So this is a recovery here in a nutshell. Karen's laptop notices that, and so it requests that segment to be sent again. Now, if you look at adjacent layer interaction, same layer interaction, what's all this about? Well, in this same example here, we see adjacent layer interaction and same layer interaction. So adjacent layer interaction means one layer of the TCP/IP model interacting with a high layer, and we can see that the transport layer, which is this what TCP recovery is belongs to, the transport layer. This feature is interacting with the application layer request, which is for that web page, the HTTP request. The HTTP request and TCP recovery, they're working hand in hand here, because for a successful web page to delivery to Karen's laptop, for her to receive that pizza restaurant menu, she needs her laptop relies on TCP recovery to tell in order to identify if the full web page contents have been received or not. And so this is TCP recovery and HTTP working hand in hand here. So TCP recovery is serving the application layer to in order for the successful delivery of the web page, because it's all about, at the end of the day, the user experience, the application. So that's adjacent layer interaction. Same layer interaction is what we're seeing here, where you've got the error recovery working on both sides. Error recovery works on both sides, but error recovery has to work on the web server and it has to work on the laptop in order for this error recovery to work. But the fact that error recovery and is working and assisting basically is the TCP in its, and TCP's features like error recovery are there, and they exist, and they're working, and they're supporting the application request. That's adjacent layer interaction, because that TCP is serving the application at the end of the day. It's ensuring that the application layer as request, the application layer is fulfilled in its requirement. So moving on, TCP/IP network layer. And the network layer uses the IP protocol to forward IP packets between devices. So this is where IP addresses communicate on. The network layer is where routers communicate on, and the data form that we use here is the IP header, and we use the IP protocol, and we have got the IP header. Sorry, the data format is the packets, but the IP header is what is carrying the IP addresses, the source and destination IP addresses of the packet are carried in here. So the data format is the packet, like in transport layer is segment, and when we move on to data link layer, it's frame. And so data link layer communicates in frames. It breaks down IP packets into frames, and this is through a process called de-encapsulation. So if we look here, this is Karen's router here, and this is the pizza restaurant server. Now we see encapsulation here, where we've got the packet being sent, and it's being attached with, is being encapsulated with an Ethernet header and Ethernet trailer. And then this is, and now we have from encapsulation here, we're going to transmission, then it's received the Ethernet header, IP packet, and Ethernet trailer together, received by the packet, and the packet extracts, received by the router, and the router will extract the packet, okay, discarding the Ethernet header and trailer. So those discarded, and the packet is received. Okay, so the Ethernet encapsulation refers to adding headers and in some cases trailers around our pieces of data that make up our pizza menu web page. Now, finally, the physical layer. Now, the physical layer is the physical hardware, cables, and signals that deal with the physical aspects of network communications. It's the physical hardware, cables, and signals that deal with the physical aspects of network communications. Okay, so it's is all those physical things that are making our networks work. So this is also referred to as layer 1 in the TCP/IP model and the OSI model. So that brings us to the end of this session. Thank you so much for watching. I hope you enjoyed this. Hope you learned from this video. If you enjoyed it, please like, share, and subscribe. Thank you so much. Cheers.